picking up good vibrations.
We have seen before that we can represent a signal x of t as an integral from minus infinity until infinity of x of s delta t minus s ds, where delta is a direct function. Intuitively, we are decomposing this continuous time signal just as we did in discrete time with impulses, but this is hard to see since an impulse in the continuous time is a very non-intuitive function. However, if we recall the definition of an impulse, it is the limit of a class of rectangular functions. So instead of decomposing the signal in terms of impulses, we are going to decompose it in terms of these rectangular functions that have a width capital delta for a fixed capital delta. In other words, we are going to approximate this integral by a Riemann sum, and this is why we see the delta factor at the end. These rectangular functions have a height 1 over capital delta, and since they multiply by x of k times capital delta, then the resulting product has a height of x of k capital delta. So for any continuous signal, I can always take some evenly spaced samples, multiply by one of these rectangular functions with constant height capital delta, and obtain something like this. And if we let capital delta go to 0, then this approximation will be more and more accurate. Now, we follow the same reasoning as we did in discrete time. For discrete time signals, we know that if the system is linear time invariant, the output responses to a shifted signal will be the shifted versions of the responses to the initial signals. Nothing new so far, but now there is a subtle thing I'd like to ask your attention for. If we take the response of the system to a rectangular function with capital delta, so those rectangular functions that define a dirac, we get something at the output. But this output will be different depending on the width capital delta. Now, for a very broad class of systems, and those that we're going to focus on in this course, if we let this capital delta go to 0, these responses will start looking all the same. So as capital delta goes to 0, there will be a limit. So the limit is well posed, is well defined, and we can call that limit, as capital delta goes to 0, the output responses to this rectangular function as capital delta goes to 0, we call that limit the impulse response, and we denote it by h of t. So, given the decomposition of the signal into the sum of the subsignals defined in terms of these functions that define the dirac, if we apply this signal, which is the sum of these basic rectangles, to a linear system, we will get as output a weighted sum of individual responses to each of these rectangular subsignals. Now, you can notice in this formula that this looks like a trapezoidal approximation of an integral, a Riemann approximation of an integral. In fact, we have here a summation of values of the function spaced by delta times the function spaced by delta, and they are multiplied by delta. If we take the limit as this parameter capital delta goes to 0, we get this integral here. And this integral is known as the convolution integral. This convolution integral only depends on the impulse response h. Therefore, as in discrete time, it is enough to characterize the response of an LTI system to any input, and so the impulse response h of t fully characterizes the system. Just as in discrete time, if the signals are 0 for negative time, the expression for the convolution is also simpler here. We can first simply replace in the formula the lower limit of the integration that is minus infinity. We can replace it by 0 since x of s is 0 for negative s. And then since h of t minus s is 0 if s is larger than t, the argument then becomes negative. We can replace the upper limit by, which was before infinity, we can replace it by t. Also here, if the system is causal, we must have an impulse response which is 0 for negative time, so this formula is very important in many cases.